Hello, my name is Lorenzzo Mantovani, and I will present the paper Reinforcement Learning for Satellite Autonomy under Different Cloud Coverage Probability Observations. So first, I'll talk about the Agile Earth Observing Satellite Scheduling problem, and we can break it down in some parts. So Earth Observing Satellite corresponds to a satellite, in this case in low Earth orbit, with some sensing instruments. Scheduling problem is finding the best sequence of actions to fulfill our goals with the considering the system's constraints, while Agile is a satellite that can maneuver about and along track. And in this paper, we are accounting for cloud coverage because it can degrade the system performance, it can obscure an area of interest, it can use storage space that could use for some other images, or also you are spending resources, you are maneuvering your satellite to take that picture. So, for example, the mean cloud coverage in the Landsat acquisitions was more than 30%, even using a long-term acquisition plan to minimize and mitigate that problem. So, we are trying to maximize the cumulative value of unique imaged targets. We can just take one image of each target, and we are considering the cloud coverage above each target. We are also accounting for power constraints. Related work sometimes lack the use of high fidelity simulation and constraints, so they are approximating maneuver times or the power consumption. Sometimes they use simplified cloud models, or it's not possible to deploy those methods on board. So in this work, we are using deep reinforcement learning that allows for onboard decision making. It's very fast to evaluate the neural networks after training, and we are accounting for we using high fidelity simulation and constraints and using historical cloud data. Also, we are comparing the impact of different observation capabilities on our trained agents. So, how we formulated the problem? We formulated it as a partially observable Markov decision process. So the satellite can pick 33 actions. One of them is charge. The other 32 actions corresponds to imaging one of the 32 upcoming targets. And the observation space is a subset of the state space and has information that are available to the satellite and also that helps with the decision-making process. It has information about satellite states, position, velocity, information about charge levels, battery levels, when the next eclipse is going to happen, and also information about targets such as position, priority. Priority varies from 0 to 1 and corresponds of the represents the importance of the target. Also, the satellite can observe the cloud coverage forecast and the confidence in that forecast. That's the standard deviation of that. We also have power constraints, so the satellite must keep a positive battery level at all times. If it reaches 0 or below that, it's a terminal condition and we will end the episode. So our simulation environment was implemented in BSKRL. BSKRL combines Gymnasium, that's a standard Python package for reinforcement learning, with Basilisk, that's a software for spacecraft simulation. It has a Python interface, but it's very fast because it's written in C and C++, so that helps a lot during training. It has a modular configuration and flight-proven software. And we are using reinforcement learning with deep neural networks, so deep reinforcement learning. We are using an algorithm that's APPO. It's a synchronous version of PPO that's available with RLlib, and it will provide a policy that maps states to actions. One of the advantages of this method is that it works with complex constraint and dynamics, and it's fast to evaluate after training. It's less than 40 milliseconds in my laptop. One of the disadvantages of this method is training cost. It's about 12 to 14 hours. So in addition to BSKRL, we are accounting for clouds using two different cloud models. We have historical cloud data. It's from the ERA 5 dataset, and it has more than 50 years of hourly cloud data with 15 minutes discretization in latitude and longitude. So the first picture here is, first image is showing the cloud coverage over the world using dataset. And the second one is the after assigning cloud coverage for each of the targets using interpolation techniques based on the data from the dataset. In addition to the historical cloud data, we have a stochastic model. It's easier to train with because you don't need to store large data sets. And it also preserves the average cloud coverage that we saw in the dataset. One of the main differences is that we don't have spatial correlation, so in historical cloud data, targets that are very close together, they will have a similar cloud coverage. And that's not true for a stochastic cloud model. They can have very different cloud coverages. So you can refer to the paper to learn more about this stochastic model and how we constructed that. So that I showed is the true cloud coverage that is assigned to each target, but the agent never sees that information. In reality, it sees the cloud coverage forecast. And in this paper, we are providing this forecast. We are obtaining this forecast using a normal distribution about the true cloud coverage of each target. But the advantage of this method is that these forecasts can be provided using standard weather forecast models and transmit that using ground stations, or you can use onboard short-term forecast as some papers are investigating, or even some look-ahead instruments. So this information can come from different sources. We are also looking at binary reward functions and linear reward functions that are commonly seen in other papers. In the binary case, we are just going to reward the priority of the target if the cloud coverage is below a threshold. In the linear reward function, it will just decrease linearly with the cloud coverage. So here we have a short animation of what the simulation looks like. We have the ground track of the satellite in red, and you can see that it's targeting some targets and it will attempt to image. Those black dots mean that the target is actually covered by clouds, and the red dots are images that were successfully acquired and have a cloud coverage below the threshold. So the results now, we consider 5 different agents that have different observation capabilities. CloudSat CF and Sigma can observe the forecast and standard deviation. CloudSat CF can only observe the forecast. CloudSat Sigma only that confidence in the forecast. CloudSat cannot observe any information about clouds, but it was trained without clouds, which means that the reward function accounts for the true cloud coverage. The normal set cannot observe any information about clouds and was trained without clouds, so a completely cloud-free environment. So we have 5 agents, 2 cloud models, and 2 reward functions, resulting in 20 trained policies. The cases trained with historical cloud data use information from 2011 to 2022, and all agents were tested with historical cloud data, including those trained with the stochastic model, and use information from 2023. So first I'm going to show the results for the binary reward model. In this case, we are introducing the normal set pre-filtered as a comparison here. It's the same as the normal set that never saw clouds before, but you can think of it as the ground station filtering the targets before passing them to the satellite based on the cloud forecast for each target. And here the threshold for filtering is the same as the binary reward model, that's 0.2. So what we see in these results in terms of reward is that agents that can observe the forecast have a better performance, while the cloud set and normal set have similar performance in terms of rewards until 6,000 targets, then normal set starts to perform a little bit better. In terms of cloud-free metrics that measure the percent of images that are cloud-free, we see that agents that can observe the cloud forecast have much better performance, and agents trained with historical cloud data have an even better performance. But so far, uh, in terms of reward, agents trained with stochastic model and historical cloud data have an equivalent performance here. We can also look at the targets that these agents selected in terms of priorities, and we see that the normal set selects targets with the highest priorities, while the agents that can observe the forecast select lower priorities. And the cloud set that cannot observe information but was trained with clouds is somewhere in between. On the other hand, agents that can observe the cloud forecast tend to select agents with the smallest amount of cloud coverage. On the other hand, agents that cannot observe that information tends to have just a value that's closer to the average cloud coverage. But something that's interesting here is that the normal set has worst resource management. It has the lowest average battery levels across all simulation cases. all test cases, compared to all other agents. So although they have similar performance to Cloud Set, normal set has worse resource management. And in the paper, we go into more details about why this happens and why the cloud set ends up having a policy that's better suited for environment with clouds. Now, comparing the results for the linear reward model, they are actually very similar to the binary reward case. One of the main differences here is that agents, the dashed lines that are agents trained with stochastic model, outperform agents trained with historical cloud data. And that happens because we are introducing more variability and different scenarios. We are exposing the agent to more diverse cases during training using the stochastic model when compared to historical clouds data. Still, the agents trained with historical clouds data, they have a better results in terms of cloud-free metrics. So just a quick summary of our results. Agents that can observe cloud information have the best performance. Training with stochastic models show comparable performance to historical cloud data or even better for the linear reward case. And also, training with clouds lead to better performance even if you cannot observe that information. So in future work, we aim to incorporate different cloud thresholds for each target and also include more constraints such as storage and reaction wheel momentum management. Well, thank you for your attention.